Good morning. So thank you for coming back. This morning we'll be starting with Pierre-Yves Strub from Meta, who will be talking about computer-aided cryptography.
Okay, thank you. So hi. So yes, so I'm Pierre-Yves Strub. I'm a research scientist at Meta. So I'm applying now formal methods for a bit less than 20 years. So this is my link to that conference. So I'm not a mathematician. Okay, I know some mathematics, but I'm not a mathematician. I'm not a cryptographer also. I know a bit of cryptography, but I'm not a cryptographer, and I don't do AI. But I am interested in automated proofs by any means, meaning automated proof is an old field. Okay, it is in the field for 40 years, 50 years, even more if you think of decidability in logic. And AI might be a way to achieve better automation. I don't know, and this is my take on this. Okay, and so what I want to present today is another field of application of formal methods. So not to mathematics, pure mathematics, but to the study of cryptographic primitives, from mathematical models, so security at an abstract level, down to bare metal, so down to the assembly implementation, where you want to protect yourself against an attacker that is going to do probes on your chip. So you are going to dive from abstract models down to the computer. So first, what's the motivation of that work? Why I want what we want? Because we are numerous. It is a long-term project. It's a 10-year long project that I'm going to describe today. So what was the motivation? So the motivation is that in cryptography, there have been two crises in 2 decades. So in the 90s, basically, cryptographers realized that in the computational model, so where basically everything is a bit string, okay, it's very concrete, they don't have proof techniques to do proof of security. Okay, they are missing a way to structure their proof on paper. Okay, and so they came with a notion of game hopping proof that I'm going to describe later. Okay, but this was not sufficient. Okay, so they have this new way of structuring mathematical proofs for security. But even with that, in the 2000, okay, at the very beginning of that century, if you take a paper in cryptography at random and check the proof, you have a high probability of finding a bug in the proof or in the statement or in the primitive. Okay, so this is a problem because I'm not going to advocate that cryptography is important. Okay, in a society we have a lot of communications. We want to protect data. We want we don't want the data to be malleable. Okay, so we want hashing functions anyway. So we want cryptographic primitives that are secure. And even though, if you look at research in cryptography, you see that more than half of the paper are broken. So this is a problem. And also me, at that time, as a young research scientist in computer science and in formal methods and in logic, it was an ideal target. Okay, you have programs, you have specification, verification. So we will see that we will use code-based approach. Okay, so we will lift program verification approach to cryptography. And okay, you have security proof. So it was ideal. Something that is a bit special here is that most of the time when you speak about program verification, you speak maybe about very big programs. Okay, you want to check the system of the line 40 of the metro subway in Paris. Okay, so you have a big system and you want to check that the system is not going to crash. In cryptography, we have very small programs, 3 lines, 4 lines, 5 lines. Okay, but this is complex. The programs are going to be probabilistic, and you have multiple facets to that. So the goal here is to develop 2 assisted methodologies for helping the design, okay, so the analysis and the implementation of cryptographic constructions. So either primitives, encryption, hashing, or protocols like TLS. Okay, so protocols are built, so they allow you to communicate, and they are going to be built on primitives. So the final goals is either having automated analysis at the symbolic model most of the time, or searching for attacks, One of the goals also is to have independently verifiable proofs. Okay, so this is linked to the referee dream, where you have a proof. What you do is that you run the program, and the program is going to check the proof, and and you're happy. You are happy, and the proof, if you think the proof is verified independently of the guy, the man or woman that wrote the proof, okay, by the machine. In cryptography, you have this notion of adversary. And the people that define the cryptographic primitives and that wrote the proof is really an adversary to you. Okay? It might attack you by defining a cryptographic primitive that is incorrect and by providing an incorrect proof, but not because he made a mistake, but because he made a mistake on purpose to trick you. Okay? So it can be a state, it can be a company, anyway. So here, when you want to verify a proof, you are verifying a proof against an active adversary, not a passive adversary that make a mistake because, okay. Then you want to verify the implementations, because an attacker is not going to attack the math, okay? An attacker is going to attack the implementation. Maybe through the math, because if you have a mathematical weakness in your primitives, you are going to attack the implementation through that mathematical weakness. But sometimes you are going to attack the primitives, the implementation, relying on weakness of the implementations. I'm going to describe this later. Okay. And sometimes you want new design, better implementations. Okay. And so, as I said, I'm going to build this on formal methods. So I'm going to use program analysis, program verification for correctness, compilation for optimization of the program, program synthesis. So I have a specification. I'm going to synthesize a program that is going to be correct by construction. And so the benefits of that is that we are going to have higher assurance. We are going to have a smaller gap between provable security and crypto engineering. So the idea here is that that's the same. Okay, when you do provable security, you do this at an abstract level. And crypto engineering, I'm going here to speak about implementations. Okay, and there is a gap. Okay, and what we want to do is to close the gap. Okay, to bring the security proof down to the implementation. Okay, and to have more and more complex adversaries. More and more concrete adversaries against the primitives. Okay, and the more your adversary is complex, the more the proof becomes hard to do. Okay. Anyway, so it's a long-term goal. Okay, as I told you, it's a 10-year long project. And the final statement that I want, okay, is that one. So it's a high level, okay, it's not formal at all, but this is what I want. I want, okay, so you have a primitive, and I want that for any adversary that breaks the assembly code. Okay, so my adversary is breaking the implementation. Okay, if the assembly code is safe and leakage resistant, so meaning my assembly code is not going to crash because it is going to do invalid memory access. Okay, and it's leakage resistant, meaning that my implementation is not going to leak side information about the secrets, for example, via difference in time of execution, via difference in power consumptions. Okay? So if my assembly code is safe on leakage resistance, and the assembly code correctly implements the algorithm, meaning the high-level description of my security, of my primitive, then there exists an adversary that breaks the algorithm. Okay. And then we will do a proof of security of the algorithm. And when you compose the two, it means that you cannot have an adversary breaking your assembly code. Of course, in the model. Okay. So there are some attacks that you won't be able to capture. For example, I take a gun, I ask you for your password. I'm not going to capture this kind of adversaries. So there is a model. Okay. And there are some primitives that are secure in one model and insecure in some other model. Okay, so there are a lot of projects. We are not the only one working on that. There are a lot of projects, so you have security in symbolic and computational model. Okay, so me, I'm going to work in the computational model where everything is a bit string, so it's super concrete, but then you can have a more abstract model, symbolic model, most of the time for protocols, where basically you have parties exchanging terms in some algebra. And then you have a lot of tools here. You have Provary for doing automatic proof of security of protocols in the symbolic model, Tamarin for searching attacks, Cryptography for doing automatic proof in the computational model, EasyCrypt that I'm going to describe later, F star, that is a lot at Microsoft Research. Then you have tools for doing side channel analysis. So you want to check whether your implementation is going to leak information about your secret via time analysis, power consumption analysis, etc. Then you want to check for safety, so you want to check whether your program is going to crash or not, because it is going to do buffer overflow, invalid memory accesses. Okay, you want to check for functional correctness, so you have tools for this. So you have Concert, VST. So Concert is a compiler for the C that has been checked in proof assistance, in the code proof assistance. Okay, so it is proven correct. You have Cryptol, so here you want to check that your program is implementing what it is intended to implement. And then you have tools for cryptographic engineering, for writing specification, for examples. Okay, and so we have different case studies. So this one starts to be a bit old, but it does everything. So I'm in CBC, I'm not going to enter into details, but then currently we are targeting a large proportion of the participants to the NIST contest for the post-quantum cryptography contest. Okay, so before describing how I'm going to formalize a proof in cryptography, I'm going to tell you how you do a proof of cryptography and how you define a security notion. So the broad idea is that one. You have a definition, okay? So it's cryptography, you see, this is going to be your your cryptographic primitive, sorry. And that definition is going to be constructed over an assumption. Okay, so it is going to use an assumption, so to use some basic blocks on which you have an assumption. Okay, so for example, it could be a discrete log, and the discrete log is hard, but it could be that you have one-way functions that are hard to invert. So you have a cryptographic assumptions. And then you assume that you have an attack against your definition. Okay, so you make that hypothesis. And what you are going to do is that you are going to build an attack against the assumption. Okay, and the way you do this is via a reduction, meaning that you are going, so the attack on the top of the slide, so the attack against the assumptions is allowed to use the attack against your definition as a black box. So now you have two solutions. Either the assumption is not hard, okay, because you have some restriction over the attack. So you make some, so the attack, for example, you will enforce that it is a polynomial time Turing machine, okay. So you are going to restrict the power of your attacker, okay, to something that is sensible, okay. And so now, either you have an efficient algorithm breaking your assumption. So for example, you manage to find a way to do factorization in prime factors efficiently, okay, right? Or the first attacker, okay, the attacker against your definition cannot exist. Okay, because if it exists, then you can break the assumption. The assumption is not possible. Okay, so let's now zoom on that diagram to see how you do this more concretely. So I'm going to use, as an example, a public key encryption. Okay, so this is an algorithm for doing encryption where you have basically a public key, a secret key, and what you can do is that you can use the public key for doing encryption of messages, and then you need the secret key for doing the decryption. Okay, so it's an algorithm with three parts. You have key for the key generation. So this is a probabilistic algorithm because each time you run the algorithm, you want a different key pair. Okay, you have epsilon, that is the encryption. So the encryption most of the time is probabilistic. Okay, so basically because you don't want when you encrypt the same message twice under the same key to have the same cipher, otherwise you won't be secure in the CCA model, for example. And then you have D, that is the decryption, and you see that epsilon E is parameterized by the public key, PK, and D is parameterized by the secret key, SK. Okay, and D is deterministic. In that case, it is going to be deterministic, and it is partial, okay, because sometimes you will give a message, a cipher, that is not a valid encryption. Okay, so you want that equation, basically the decryption of the encryption of a message is that message. And now, okay, you want to define what is an attack against a public key scheme. Okay, so I want to define, so okay, I want to build an attack against my definition, okay, but I have to define what is an attack against my definition. And so here, again, you don't have a single definition. First, it will depend on the kind of primitives you are studying. The definition of security for encryption or for hashing or for signature is not the same. And even when you are studying, for example, encryption, you may have different definition of security. It will depend which one you prefer, which one also you can reach. So here I'm going to describe one experiment, the INCCA experiment, so indistinguishable under chosen ciphertext attack. Okay. So this is one of the oldest definition. And basically, so you define what is an attack via an experiment, here that game. So a game, an experiment, a program is going to be the same thing here. So you have this game that is taking as a parameter an adversary, so that is trying to break. And that game is going to control the interaction between the adversary and your primitive. Okay, because the adversary cannot do what it wants. Okay, because otherwise the adversary will just open the memory, read the key, and it's done. He won. Okay, so the game is going to control. Okay, so you have this this control, and here is what it is doing. So first, you generate a key pair, S key, PK, and you give the public key to the adversary. And the answer of the adversary, the adversary is going to give you two messages. Okay, so at random, or two fixed messages. The adversary is any program, polynomial program here. Then the experiment is going to flip a coin. Okay, and depending on the result, head or tail, it is going to encrypt the first or second message returned by the adversary. Okay, and then, yes, so this is this. Okay, and then you give that all of the adversary is to guess the bit that you sample. Okay, is to guess whether you had a tail or a head when you tossed a coin. And the adversary wins if the guess is correct. Okay, so this is the definition of my experiment. And now I have to say what is a proper attack, because the adversary can win. Okay, sometimes you just adversary here for B prime, you just flip a bit at random, or you always return false, or you always return true, and the adversary is going to win with basically a probability of half. And so what you want is that for any adversary A, the probability in that game that B equals B prime minus 1/2 in absolute value is small. So basically the adversary can win, okay, but not with not a probability that is different than the adversaries that just do a random sampling for B prime. Okay, so now, so here an example, OEP. So basically OEP is an algorithm for lifting a one-way trapdoor function. So one-way trapdoor function is a function, so it's a family of functions. It is parameterized by a public key. Okay, and then you take a big string. You return a bit string. Okay, and that function is hard to invert. Okay, so think about RSA. Okay, so F is easy to compute, but it's hard to invert, meaning what it is to be hard to invert is that basically you need, for example, in polynomial time, you cannot invert F. But it is a trapdoor, meaning that if you know the secret key, then now F is easy to invert. Okay, so it's a one-way function with a trapdoor, the secret key. Okay, and so think about RSA. Or RSA is a one-way trapdoor function. And these OOP schemes allow to lift a one-way trapdoor function to a public key encryption system that is CCA secure, because RSA is not a secure encryption system. So the first time I read this, I was shocked because when you do a crypto course, RSA is presented as a system for doing encryption, and no, it's not. It's a one-way trapdoor function. Anyway, so you have the encryption scheme, okay? So you see it's a 4-line function. You have the decryption scheme, it's a 7-line function, maybe. So these functions, sometimes they will use external oracles. So this function, for instance, they need to compute hashes. And so either you use a concrete hash function like SHA-3, but then you are in the standard model and the study is very complicated. Here I'm going to focus on the random oracle model, where basically the schemes, the adversary, they have access to oracle that implement perfect hashes function. Okay. And then you have a game here in gray, and that game basically is assessing whether you are able to compute the pre-image of F without knowing the secret key. Okay. So basically that game in gray is assessing whether you are able to invert F. And so now the final statement, okay. Okay, so the reduction from my attack to my assumption, because my assumption is that it is hard to invert. And so the final statement is that basically, for any adversary, the probability that my adversary wins the CCA game, minus 1/2, okay, is bounded by the probability of inverting that. Okay, plus a big formula. Okay, and so that formula depends on the number of calls you do to the oracles. So you can, this is negligible. Okay, when you do concrete cryptography, you have a concrete expression, but then you can do asymptotic cryptography, and then this is negligible. And so you see, I don't say that this is hard. I say that if this is hard, then the probability that the adversary wins against CCA is going to be small, because the right part of that inequation is going to be small. Okay, so remember we have this function. This is the full scheme. Okay, so very small program. And it took 15 years to come with a correct definition and a proof. Okay, so the first definition was in 1994, and then basically you have a full story with different papers. So it was a chain of paper publication. Okay, you correct the previous paper, and then you correct the previous paper. And so sometimes you say, okay, there is a bug in the proof, you fix the proof. Then you say, no, there is still a bug in the proof, but in fact, we cannot fix the proof. We have to change the definition of the scheme. We have to change the definition of one-way trapdoor function. We have to move to partial one-way trapdoor function. Okay, and then there is a gap, and then you see that, yeah, the security definition has to be clarified. It's not super clear. And then there is a final paper in 2011 where you have the final proof, the final definition.
This is not formalized, right? This is
no, it is formalized.
is it formal?
2011 is the formalization of the proof.
The formal
So, yeah, this is where we arrived. And so maybe if we were not there, maybe one slide would not be sufficient to write that listing of bugs. So 15 years. And for this, so either cryptographers are plain stupid, but no, I don't think so. Either there are subtleties, okay? Okay. Anyway, the conclusion is that we can do something because we know how to, meaning we have methodologies, informal methods to tackle these problems. So the first answer to that was a Coq library. So Coq is a proof assistant. Okay, it's like Lynn or Isabelle. Okay, it's here since the 80s. Okay, and so the first solution to that was to define a Coq library where basically all what has been described just now has been formalized, okay, as mathematical statements, and then you do the proof. So this was horrible because the tooling at that time was not the same. Because you have to define your programming language, you have to give the semantic of the programming language, meaning it was very hard to tackle. So what we decided to do is to implement our own theorem prover named EasyCrypt. And basically, EasyCrypt is a domain-specific proof assistance. Okay, and so it's an Isabelle-like proof assistance with matcomp SSRefect-like tactic language. So it's a domain-specific proof assistance, but still you have a higher order logic, so you can do the math you want in EasyCrypt. But then in EasyCrypt you have a primitive notion of what is an algorithm, a probabilistic algorithm, and you have dedicated tactics to do program verification. Okay, so I can give a very small demo. No, not that one. No, not that one. Okay, so I don't know where it is. Here it is. Of EasyCrypt, maybe it's a bit small. Maybe also you see nothing, in fact. I think I have to.
Is there a 3 small or not?
Yes. I'm going to mirror, I think. Okay, now it's small. But the idea is the same as that you saw yesterday. So you have this file, and the difference is that you see you have a primitive notion of what is a program. So here I have two programs. I have one program fair that is basically just doing a random sampling, okay, in bool, uniform sampling. So these programs are abstract because I can sample in any distribution, okay, which is not feasible in practice, in bounded time anyway. And then I have a program that is simulating a fair coin toss for a coin, for a bias distribution, okay, a fixed bias distribution. So I have a distribution of Booleans with a bias P, okay, between 0 and 1. And what I want to do is that I want to simulate a fair coin toss. And so what I do is that I'm going to toss my coin twice. And if the results are the same, I'm going to reject the sampling. Okay, I'm going to do this again and again and again. At some point, I'm going to have different results, and then I return the first or second toss, whichever. And so this is the same. This is going to do the same thing. This is going to terminate with probability 1. So everything is discrete here, okay, only discrete distribution. So this is going to terminate, and the result is going to be true with probability 1/2, false with probability 1/2. And so I'm not going to enter into details, but basically, that's more or less the same. You have tactics, so you can write statements, so it's unreadable. So here it's a very simple mathematical statement about some distribution, and then you can apply tactics. So here this is a one-liner, and at some point the system is going to be happy and to tell you, okay, it's okay, your proof is correct. Okay. The difference is that you have program logic. So basically here what I say is that I took these two programs, sample, fair, to do sample, okay? And then I'm going to write a precondition and a postcondition, okay? So the precondition is the assumption you made about the memory before executing the functions. So here you have two memories because you have two programs. And the postcondition here, which is equal res, is what you want to prove about the output memories. So here what I say is that the result for the first program is going to be equal to the result of the second program. And here the assertions, they are over memories, not over distributions, because they are going to be lifted to distributions. Okay, I'm going to explain this right now. And then you have tactics, and so I'm not going to enter into details, but you see you progress, and you have goals, and you progress. And in the end of the day, you are happy, and you prove that the program are equivalent. Okay, so more here, but anyway. Okay. So I'm going to stop memorying and to restart. And I'm going to speed up. So I'm going to go very fast. So basically, so what we realized, so we defined these logics, okay? We were very happy, and what we realized that basically what we were doing is to construct probabilistic coupling, so meaning you start from two programs which are probabilistic, and in fact you construct a program, a product program in the product of states, okay? And so what you build is probabilistic coupling, and this is well known in math. And here what we are constructing are monotonous coupling, so meaning it's the coupling whose range is included in the postcondition. I'm not going into details. What is important here is that, for instance, if your postcondition, if your relation R here is equality, and you build a coupling monotonous for equality, what you encode here is that for any event, the probability on the left memory and the probability on the right memory, the output distributions are the same. Okay, so by using these program logics, by using assertions on memory and lift up to distributions, we are able to encode properties about probabilities. Okay, so we can equate probabilities, we can encode inequalities, comparison of probability of events. So basically, we are able to encode this. Okay. But the idea is that, so this is not new. Okay, we just realized that we're using something that is well known, in fact, but this allowed us to better understand what we are doing and to generalize this for other domains. Okay, but the idea of having here, so where it is, of having, meaning assertions over memories, is that we are going to reuse programs that are doing program verification. Okay, so the idea was not to come with a new logic where you have assertions speaking about distributions and where you have to redefine everything, but instead to be able to reuse techniques and to reuse tools from program verification, because program verification is here for now 40 years, 50 years, okay, and so you have a lot of tools. These tools are now well established, so we wanted to be able to reuse them. Okay, so here's the formal definition of what is a program in EasyCrypt. Okay, I'm not going to enter the details, it's not very interesting. I just want to give some ideas of what you can prove. So basically, once you gave the definition of the semantic of your program and what is for a program to be correct with relation to some specification, then you have rules, and you can think about this rule you can see these rules as tactics. So basically, you want to prove something, and you apply a rule, and these rules are correct, okay, of course, so meaning when you can prove something, that thing is valid, okay, and so you can apply them, and you can progress. Okay, so these rules are like tactics, but not in Zermelo-Frankel set theory, not in type theory, but in program logic, in a logic dedicated to program verification. Okay, so here you have two examples, but I'm not going, the details are not interesting. Okay, so the status is that now the tool is 10 years old. It has been applied to quite a lot of application, encryption, signature, hash design, key exchange protocols, zero-knowledge protocols, cable circuit voting, and now post-quantum schemes. We found a lot of bugs and subtle bugs in the proof and sometimes in the scheme. So this is useful, meaning we really found bugs. But it is interactive, and this is time-consuming and difficult to use. And sometimes because, okay, there is something subtle to solve, but sometimes because we are dealing with programs, okay, especially when we are going to speak about an implementation, and then you have side conditions that can be huge, okay, but not interesting at all. But when I say that they are huge, is that maybe there are 50 lines long, okay, big expression with maps, modular arithmetics, linear arithmetics, and here solvers, state-of-the-art solvers, are not good at discharging them. So we have to do them by hand. Okay? And this is time-consuming. And I think when we do a proof, 20% of the time we work on the interesting parts, and the remaining 80% we work on the side conditions. And this is where really I want to see whether AI could help, really. Because I want to just remove this 80% from my site. Okay, I want them to be automatized. Still,
But it is the side conditions where the attacks come, right?
yes, yes. I don't want to admit them, but I want a program to solve them for me because they are not interesting, but they are hard to do because dealing with a statement that long is hard. But that's all. Yeah. Still, you can still use these tools with a lightweight approach where you don't solve the side conditions. Okay, you write the games, you write the intermediate games. Okay, you write the statements, you write the important part of the proof. So it's not bulletproof. Okay, you can maybe the attack are in the side conditions, but then here the tools are easier to use, and here you will catch some problems. Okay, but anyway, we need automation. Okay, so how this proof could be automated? So one part is for the side conditions, and then there is also, but this is more long term, maybe we could also automatize a bit these high-level parts. So in a reductionist proof, I will have the starting game, the ending game, and then I will do game hopes, and I will do maybe 2, 3, 4, 5 game hopes. And some of them are standard, and they are tools trying to find for you these intermediate games. Or they are going, or you give 2 games, you give the attacker against the first game, and you want to infer the attacker against the second game. Okay, so this is something that you do. Okay, and maybe here too, it will be possible to automatize this. Okay, so this is a guess game. Okay, so you want to do a reduction, you guess the adversary, and then you check the equivalence. And so maybe here automatization means that you write the game, and automatically you check the equivalence, or a program gets the adversary for you, and then you do the proof, or both. I don't know. But here there is some space for doing automation. Okay. And so now I'm done with high-level proofs, and I'm going to move to implementation. Because what we want is that we want secure crypto primitives, but now we want them to be fast. So for example, for public key encryption is super slow, okay, with relation to symmetric encryption. Okay. But see, we want them to be fast. So what it means that most of the time the primitives are going to be written in assembly using vectorized instructions. So we want them to be correct when we want the implementation to implement the algorithm. You want them to be side channel resistant, so we don't want to leak information about the secrets by side channels. And we want them to be secure, so we want to transfer the security proof from the high-level proof algorithm to the implementation. And so as I told you here, you have a choice. Either you are going to use a high-level programming language. So here, high-level programming language is C. So because for example, if you take OCaml, you have the GC. The GC is totally going to kill constant time, for example. Sorry? Garage collector. So the program that is responsible of freeing the memory for you. So here high level is C. And so C is portable, much more portable than assembly. Okay, it's co-reinforced because you have abstractions, and it's readable, maintainable. Okay, but assembly you can write much more efficient programs. Okay, we are speaking about small programs, so really you can optimize them a lot, and you can have much more efficient implementations. You have control, full control. You can select the instructions that you want to use, okay, and it's predictable because you don't have a compiler between you and the machine. Okay, you write directly. Okay, but the problem is that assembly is not programmer friendly. Okay. It's not verifier friendly because you lose the control flow in assembly. In assembly, you have gotos, that's all. You have jumps, but you don't have conditionals, while loops. So it's very hard to verify assembly. It's more error prone, okay? But source is not secure, efficient, friendly. You have to trust the compiler. Certified compiler works, but they are less efficient, okay? They are less optimizing, and they can break some properties. Some optimization can break properties. So we are in that state. So basically you have C, low assurance, low efficiency. So we don't want to use C. Then you have assembly, high assurance, low assurance, high efficiency. So, okay. Then you have, for example, fiat crypto or Veils. Okay, so you have high assurance because you can do proof of implementation, but you don't have efficiency. The code that you are producing is slow. And so what I want to present here is Jasmine, a certified compiler between C and assembly. So we will have efficiency and high assurance. Okay, so the idea of Jasmine, it's a high-level language with assembly in the head. Okay, so it will be programmer and verification friendly, meaning you will have while loops, for loops, conditionals, functions. Okay, so it's good for the programmer, for abstraction, it's good for the verifier. But the compiler is going to be predictable. It is going to be formally verified. So this is again an application of formal methods. We are going to check that the compiler is correct. Okay. And so the programmer is going to have control, and the compiler is not going to introduce security bugs. Okay. And some verification toolchain is going to be based on EasyCrypt, so the prover I just presented. Okay. So here are some examples. I'm going to be fast because first time is moving. But the idea is that it's a C-like programming language, but you have abstraction, but the abstraction doesn't have a cost. So you don't have any hidden cost in terms of optimization computation. So you have variable names, you have arrays, you have loops, but the loops, for example, they are going to be fully unrolled for you. Okay, so you don't have the hidden cost of having to increment the index I, and you don't have the hidden jump. Okay, the loop is going to be unrolled, and this is something that cryptographers do at assembly level. They are going to write the first iteration, then they are going to copy paste the assembly code and paste 8 times. So then you have to verify this. Okay. Of course, we also have while loops. Okay, so generic loops. Yes.
Even in such a loop, you need to know how many times it will be executed.
Yeah, but you know.
8, 15.
Yes, you know. If you cannot guess, meaning at the same when you copy paste, you need to know the number of times you are going to copy paste. Okay, so this is going to capture this. So basically, you are going to work on arrays of size where you have 8 words, and you want to do an operation on all the elements. And this is fixed by the primitive.
So you can't loop from I to J?
No, you can't. If you do this, then you have to use a while loop. So we have generic while loop. Okay, they are not unrolled. But now you are aware that you have a jump. Okay, so meaning you really tell the compiler, I want a for loop, and the for loop is going to be unrolled. And if the compiler can not unroll the loop, it is going to fail. Or you use a while loop, and then the while loop is not unrolled. But it's predictable. Well, if you write a while loop or a for loop in C, you don't know. The compiler may or may not do the optimization for you. Okay, so you have access to register, so you can say whether a variable is in a register or is in memory. You have control over the spelling. So the spelling is when you don't have enough registers, so you have to offload some registers in memory to free some registers. So this is spilling, and so you have to do the spilling by hand. Okay, so it's not C. For example, register allocation is not done for you. But it's not assembly. You don't say, I want to be in that register. You say, I want to be in a register. Okay. And of course, you have direct memory access, so you can have access to the flags. So for example, on a CPU, most of the time, when you do an addition, so it's a modular addition because you are limited by the size of words, but you have a flag, which is a carry flag that tells you whether you have a carry or not. Okay, and if you don't have access to the carry flag in C, you have to use assembly. So you can use assembly in C, but you don't have access to that flag directly. So here you have access to the flag. Okay, directly. So you don't have to do addition plus comparison. So again, it's between C and assembly. And of course, you can be really low level. So if you need that instruction, that specific instruction from your CPU, you can call it. Okay. So Jasmine is a language, and Jasmine is a compiler. So it's predictable. Okay, and you have full control over the generated assembly. Basically, when you write a program, you know which assembly is going to be produced. It preserves the semantics, so meaning, so we had to define the semantic of Jasmine as a programming language. We had to define the semantic of Intel CPUs. Okay, so it's very fun. It's 5,000 pages of super fun documentation. You should open it once in your life. And we proved in Coq, so we have a formal proof, because now we have statements, we have mathematical objects. Okay, they are speaking about computers, programming languages, but they are formal definition. And so we have a proof of preservation of semantic. So meaning that, basically, if you have a source program S, that is, if you have a memory M that is going to go to M prime when executing S, then when you do the compilation, okay, and you start from the same memory, and you execute the assembly code, you obtain the same memory. Okay, so that's the commutation diagram. This is the way you express it. Okay, and it preserves side channel resistance. Okay, so meaning, maybe I'm going to speak about this, but meaning if your source program, you can prove that you are not leaking information about the secrets, you know that the compiled program is not leaking any information about the secret. And this is an optimizing compiler, okay? So you have the main common optimization that you can expect to have in a modern compiler. Okay, so for example, constant propagation. So when you have I equals 0, x is equal to I plus 1, okay, then you just write 1, okay? Because you know that I is equal to 0, so constant propagation is one optimization. And then you have a lot of optimizations. Okay, and so the theorem, meaning the theorem basically is at 1. Okay, so this is the theorem in code, but basically this is this commutation diagram. Okay, when you have an execution there, then you have the same execution on the compiled code. Okay, so what time is it? Oh, yeah. I have 50 minutes left, something like this, yes. Okay, so now I'm going to speak, so I'm going to go even down, because now I'm going to speak about side channel attacks. So basically, there are things that I cannot capture at the EasyCrypt level. Okay, so when I have my first OLP definition, I was using random oracles, I was doing sampling in perfect mathematical distributions, okay? But now at the implementation, and really on my machine, I'm manipulating bit strings, and that machine is going to take time to execute my program. It is going to do memory accesses, okay? And maybe, okay, this measure, time measure, power consumption measure, are going to depend on the secret. Okay, so think about the exponentiation. So you want to compute x to the n. Okay, so you can just write the linear algorithm. Okay, it's going to be super slow. Or you use fast exponentiation. Huh? Repeated square the name, okay. Okay, so basically here you do recursive call and then you square. Okay, or when it is odd, you do x to the n square x. Okay, so this is faster. And in RSA, okay, you are computing an exponentiation. Okay, and in RSA, the exponent is your secret key. And now you see that, so basically you are going to access the bit of your secret key one by one. Okay, and depending on whether the bit is 1 or 0, either you do a multiplication, or either you do multiplication, 2 multiplications. Okay, and so here you are going to detect the length of the computation. Okay, you are going to see. Okay, and so you are going to infer some information. Okay, so sometimes you are going to do, depending on the secret, you are going to do a multiplication or an addition. And an addition is very simple to do on a CPU. Okay, it's basically it's a textbook addition that you saw in elementary school, but you do this in parallel. You do all the addition in parallel, then you plug the carry, okay, and then you wait for stabilization. This is a metastable algorithm. You don't do them one by one. You do them in parallel, and then the carry is going to propagate, and when it is stabilized, you have your addition. So it's super fast. Okay, multiplication. Well, multiplication is going to be slow. Multiplication, that's the same. You are going. So I don't know how the multiplication is exactly implemented on the CPU, but it's not metastable. So it's going to take more time. So the CPU is going to consume more power. Okay, and the CPU, they try not to consume too much power. Okay, so they are going to change when they need power. They are going to change the voltage. Okay, so they are going to move from 5 volts to 12 volts. Okay. And when you change the voltage, okay, so you have condensator, so it's this in capacitor. Thank you. So the capacitor, yes, you are one. We are going to the bare metal. So the capacitor, the voltage of the capacitor is going to change, and so you are going to have a vibration. And so now, if you put a microphone for listening to bats, you are going to hear these vibrations. And so basically, if your algorithm is doing multiplication or addition depending on the bit of your secret, okay, and each time you have a change in the bit value, okay, you are going to change the voltage, and you are going to hear that. Okay, and so you are going to know basically some information about your key, and at some point you are going to break it. So maybe using a microphone is a bit hard, but then you measure the voltage on your USB plug, and when the CPU is going to change the voltage, you will have some leakage here. Or maybe you can measure time. Okay, so assume that you are doing an access to an array based on the secret. Okay. So when you read in a memory, that array is going to be in a memory page, and you are going to put this in a cache line, so that if you re-access that array, it's going to be faster. But the cache line is very small, so if some other program is going to read a lot different memory pages, that line is going to be removed. And the next time you want to read in that array, you have to load it again. Okay. So what you can do is that you can manage to offload half of the array, and so that when then the crypto algorithm is accessing the array, okay, if there is a cache hit, the memory access is going to be fast. If there is a cache miss, then you have to load the array in the cache line, and this is going to be slower. But we are speaking about microseconds here, okay? And this is sufficient to break AES in a few milliseconds without any privilege in Linux. And now there are dedicated instructions on the CPU for avoiding this. So the idea is, can we reason about constant time? So basically what you want to do is you want to avoid this, basically, you want to avoid programs that are doing memory access that depend on secret, or that are doing computations that branching that depend on secret. You simply forbid that. If you forbid that, you don't have this, you don't have this. Because memory accesses, the addresses are going going to be public information. And so can we reason about constant time at the source level? Well, no, in fact. So think about this. I'm going to do only one example, but think about that function. That function is basically it's returning x or y depending on the bit b. Okay, and so you can write this. Give this to GCC or CNang, and what you have after optimization is that code, because that code is faster. Okay, and if b is secret, the first one is constant time. You see, the first one you don't do any branching based on b, and you don't do any jumps, any memory access based on b. In the second one, if b. Okay, so now clearly you are doing a jump that depends on the secret. Okay, and you have a lot of examples where optimization is going to break constant time. So, okay, so bad news, but good news is that most compiler optimizations, they are preserving constant time, but you have to check that. Okay, and so we came with methodology, formal methodology, to check that an optimization path preserve constant time. So I'm not going to enter the details because I'm running out of time. But basically, yes, we apply formal methods here to check that all optimization passes preserve constant times. So that in Jasmine, you can speak about constant time and you know that the final implementation is going to be constant time. Okay, so I'm not going to enter the details because I'm running out of time and this is not very interesting for my purpose. Okay, and so then, last step, okay, so we know that the program is constant time. We can verify constant time using EasyCrypt. I'm not going to enter the details. We know that the compiler is preserving constant time. You have full control over the assembly, so you can write efficient code. You have a security proof in EasyCrypt. And so now you want to link that implementation to the algorithm. Okay? And here again, what you are going to do is that you are going to use EasyCrypt for doing this, because basically, linking the algorithm to the implementation is doing game hops, where here you do not start from your attack to some other attack, but you start from your optimized implementation, and then you de-optimize the implementation, and each step you prove that both programs are equivalent. Okay? So here, for example, for SHA-20, you have the reference implementation, and then you optimize, or so it depends whether you read from right to left or left to right. But if you read from right to left, so on the right you have the implementation in Jasmine, okay, and then you de-optimize. So you de-optimize the vectorization, you de-optimize the skill union, you de-optimize the loop tiling, and in the end of the day, oh, this is my reference implementation, and you are happy. And then you have the full story. Okay, and again, yes, so you can check constant time using EasyCrypt. So the idea is that, again, you are going to use the program logic. So you take your program, and then you generate a program that is exactly the same, but each time you do a memory access, you record the memory access. And each time you do a branching, you record the condition. Okay? And so what you want to prove is that when you execute two instances of your program in parallel, okay, and the public informations are the same, okay, the public inputs are the same, but you don't know anything about the private input, then the output traces are the same, in distribution, of course. Okay, so equality of public inputs equals equality of leakage. Leakage is when you run your program twice. Okay, so where we are, basically, so by using formal methods, we have been able to do the proof of security of your primitive, to check side channel resistance, to have safety, to have functional correctness. Now the question is, are we fast? Because sometimes formal methods in program verification, you verify programs that are slower, because verifying optimization is something that is hard. And in fact, we are fast. We are even faster than the fastest implementation, untrusted implementation. So here, OpenSSL for SHA-20 and Poly 1305, which are new primitives for TLS 1.3. Okay, so it's unreadable, But basically, we are at the bottom. Okay, so you have OpenSSL, vectorized OpenSSL, and you have Jasmine implementation, and the line is the same. And we are a bit better because we have a postdoc that managed to win 1 or 2 CPU cycles. So I think we are winning 1 CPU cycle every 1 kilobyte of encryption, but we are faster. Anyway, and so, yeah, so finally, this long-term goal that I spoke about, we have it, meaning if I have an attacker breaking my implementation that is functionally correct, safe, side-channel resistant, then it means that I have an attacker against my algorithm, and I know that there are no such attacks. So my implementation is secure. So I'm going to conclude there. I'm not going to speak about the last part because we are not fully done, because then you have people, they can open your chip, put probes, and try to read information by putting probes in your chips. Okay? And then here we have formal methods to produce programs that are resistant to this kind of attacks up to a certain level. But I won't have time, okay? But I think the message here, what I want to do is that, what I want to say, basically to conclude, is that, so formal methods, it's now a field that is quite old, 50 years old. It can be applied to mathematics, but it can be applied to a lot of different domains. Cryptography is one domain. Every time I have a look at a domain where formal methods are applied, there is a problem in terms of scalability, especially in program verification. Because there is something in program verification is that you have huge goals. The combinatorics is very huge, okay? And there is a problem of scalability. And so you have to make trade-offs. Either you verify big programs, but you verify one property, for instance, that you don't crash. Or if you want to verify everything, you have to focus on small programs. And my reading of that is that we are missing automation. And people trying to do automation in program verification are here for a long time. And really, I'd like to see whether in the near future or far future, AI could bring some benefits in program verification, automatic program verification. And I think I will conclude there.
Thank you, Pierre, for the interesting talk. We're going to take some questions from the audience.
I just have a very naive question. This paranoid stuff here, this all goes away if you use public key cryptography, right?
No, here this is for so. Yes, here I've been fast. So here this is for private key cryptography.
So why not just use not use private key crypto? Is that
so the problem? So think about so one application is for military. Military, they have to communicate, and you have people on the field, and so they have a chip with a private key for communicating. Basically, they don't use public key. They pre-share a secret, and everybody is using that pre-shared secret. Okay. I
don't know. Is that right?
Well, I tell you, this is the way because public keys. Cryptography is not that easy. Then you have the problem of authentication of the other party, because are you communicating with a dishonest party?
I see.
Okay, so you have a problem. So you have encryption, but then you have a problem of authentication, for example. So you pre-share a secret, and then you have all these men on the field with this secret on a chip.
Yeah.
So you have physical countermeasures. So basically, you have your chip, and then you put a shell of resin, okay, and then you put some acid, and then you put a second shell so that when you will try to insert a probe, basically the acid is going to destroy the chip. Okay, but maybe you will be able to access the chip. You don't know, and then in that case you may want this. Okay, and this is not perfect because maybe you are going to be resistant to 3 probes. Okay, and so they are going to manage to put 4 probes and they are going to win. But so what you are going to do is that you are going to do very tiny chips so that when you put the probes, you are going to have electromagnetical interaction so that the reading is going to be bad. Okay? So here there are no bulletproof stuff. Okay, but still, so you have physical countermeasures and you have software countermeasures. So basically, where the idea is that your secret, you split it into T+1 shares so that the sum is equal to the secret, but they are all independent. Okay, and so as long as you are doing linear operations, you are not creating correlation, and as long as you are only putting at most n props, you are safe. And then the question is how you do when you do a multiplication. So then you have to refresh the shares, and this is costly, so you want to minimize, and then you want formal methods to put this there, these refreshing boxes for you. Okay, so that's the idea.
Thanks for the talk. I have a question regarding the indistinguishable chosen ciphertext attack in the asymmetric case.
Yeah.
I don't get how you know. So you mentioned you have two messages.
Yeah.
But how does the adversary knows? So you mentioned that you flip a bit.
Yeah.
How does the adversary knows that it has changed? Because he just has the public key. He doesn't.
No, but you have a protocol here. You see, so this is a protocol. So you give the key. The adversary is giving you the messages. Then you flip a bit. You choose the messages. You choose the encryption, and then you do a second call to the adversary, and then the adversary returns a bit. Everything is code. Okay, so the adversary returns a bit, and then the experiment is returning whether the two bits are equal. So you have really to think about, it's a program with two modules, two functions, meaning the adversary and the encryption.
Okay. But I have another question.
Yeah.
In the small demo that you mentioned, you said one time that you will flip a coin, and if I have the same answer in a row, you discard it.
Yes, and I restart.
I find that a bit odd, because it doesn't that gives you like a periodic function in some way?
What do you mean by periodic function?
I mean, if I toss a coin and I have a tail, and then you have a tail, you said that you discard that.
I discard that.
So you're.
But it's a procedure, so it's stateful. So I have two variables, and then I have a while loop.
Okay.
And then I restart. So the algorithm is basically it's y, so it's do. Okay, b received, I sample a bit. B prime received, I sample a bit. While b equals b prime. Okay. So you do this. So the question is whether this algorithm terminates, and it terminates with probability 1, and we are discrete, so it always terminates. But there is no, I don't see where you have a periodicity here.
No, okay, that way it's clearer.
Okay.
And the last one, does constant time, forcing constant time, doesn't that bring a limitation on the speed of the execution of the algorithms?
So writing constant time is hard, okay? Because, for example, this is not constant time, so you have to do Montgomery multiplication, where basically you do both. So basically, you do both operations, and then you choose the first one or the second one using CMOV, which is constant time, okay? And of course, this is slower because you are doing that extra multiplication when your bit is not, you are not in that case. So it's going to be slower, but this is the price to pay.
Yeah, it's a trade-off. I mean,
it's a trade-off.
But from a business perspective,
Yes, but constant time, meaning when you have something that is not constant time, even over the network. For TLS, you had some timing issues when the hash was invalid or not. Okay, the timing issues was in microseconds. By leveraging this, it was able to leverage 2 seconds in difference, and then you were able to extract the private key bit per bit, 1 bit per second. Okay, so no, even for business critical stuff, you want to be constant time because you have real attacks.
Yeah, I agree, but I know that you also sometimes want to have like a speed, like, you know.
So you have to work on both sides.
Yeah. Okay. Thanks.
Okay, so thank you for your talk. I just wonder if you can include in your analysis such things like a common factor attack on RSA.
Such as, sorry?
Common factor attack on RSA? Can you include it in your analysis?
Which analysis? Which one? The constant time analysis?
No. In overall approach.
Yes, so we prove nothing about RSA. RSA is an assumption.
So there was an attack discovered, like common factor attack, which depends.
So it means that you reduce to. It means that you weaken the security statement. But we prove nothing about RSA. We are not doing any. So there are works trying to analyze weaknesses in assumptions. Okay, but here we just prove that the security of the scheme reduced to the security, for example, of RSA. So if you have an attack, if you have weaknesses on RSA, yes, so you are going to have weaknesses on your scheme. But we did not tackle at all all these results on primitive cryptographic assumptions, like in RSA or discrete log in small characteristics. So you also have results. So we did nothing on that side. We just reduced to them.
Thank you.
And I think this will be something that is pure mathematics, in fact.
I disagree gently, because in a way there is a practical attack, right? A common factor attack, which eventually would be good to have it as a subject of formal analysis.
Yes, but yes, I agree this is a practical attack, but yeah. But it will be at high level, what I want to say. It will be on the other end, so I went from top to down, and it will be above that again, what I want to say.
If there are no more questions, let's thank the speaker again. We have a coffee break, so let's meet again at 35.